Well, hello everyone. Thank you for joining. My name is Francisco Castillo. I'm a data scientist here at Arize. During this panel, please ask your questions in the chat and we'll do our best to answer them in the Q&A section. If we leave any questions unanswered, we'll make sure to answer them in the Arize community. Today, we're talking about a topic that is increasingly popular in machine learning. We're talking about embeddings. Each of our panelists brings a unique perspective that will help us understand better this topic. Dylan McInnes is a mathematician and a data scientist. He works as a researcher at the Tooth Institute for Mathematics and Computing. I hope I pronounced that well. Focusing on topologically motivated methods in data science. He is well known to us for his Umap paper. On the other side, we have Christopher Moody. He is a physicist who has transitioned to data science. He has had enormous success in the machine learning industry, and he's a major contributor to open projects about machine learning. He currently works at Stitchfix as a data platform engineer, where he is leading the implementation of cutting-edge AI projects. Thank you so much both for being here, and would you share a little bit more with us about your career background and why you chose to work with embeddings, what piqued your interest? Lina, would you like to go first?
Sure, thanks. Yeah, I'm a researcher at the Tufts Institute for Mathematics and Computing. I've been there for quite a long time. I haven't been working in data science for as long. I'm really originally a mathematician, and I actually worked in cryptography for a good long while before drifting into the data science space. I have a colleague, John Healy, who I work with a lot, and he was really good at translating practical problems into mathy problems that I could understand. And so that kind of dragged me into this space. And so these days I'm sort of trying to maintain a bunch of open source libraries. There's Umap, also HDBScan, a clustering library, and Pioneer Descent, a approximate nearest neighbor library. And hopefully I can expand that set over the next few years.
Awesome, thank you. Chris?
I'm Chris Moody. I'm a scientist, engineer, and I guess maybe the best way to describe what I do now is I create algorithmic products that recommender systems. And about 10 years ago, I was an astrophysicist working on gravity simulations, and I transitioned to industry. I think one of the really cool overlaps between some of the simulations I worked with and ML was t-SNE. And it's funny because like the same numerical approximations that make gravity codes fast were the same ones that made t-SNE fast. So and I ended up contributing the Barnes Hut extensions to t-SNE inside of scikit-learn. So so that was really cool. I never expected that kind of a link to kind of exist, and that was fun. And now I'm at Stitchfix, and while here, I guess my claim to fame is I created this massively engaging Tinder for Clothes app, which we call Style Shuffle. And that was a cool vehicle for a lot of data collection, and I founded and scaled a complementary machine learning team whose role within Stitchfix was essentially to provide embeddings as a service. And that's probably like the experience I bring to this panel. But I do want to stop there and just say that like I'm really, as proud as I am about our work, I'm really honored to be here with Leland. And Leland's creator of Umap and remarkable in both the theory behind it and also like the impressively useful software engineering. So I'm excited to be on a panel with what feels like rarefied company.
Well, thank you so much. If you don't mind, I would like to start a little bit from the basics, just in case we have some folks that want to start their experience with embedding. So how would you describe the concept of an embedding to an undergraduate student, for example? Chris?
Sure. So I think two big analogies I'd like to use. One of them is, and this depends on application, but I think it helps to think of it as almost like a compressed zip file. So it's a compression of the data, usually of a specific domain. So it's in Stitchfix, the embeddings that we frequently use are, we take all the ratings that someone has liked and disliked over all the items, and then we give you a compressed embedding, which is predictive of all those ratings, right? So if someone likes a blouse and it doesn't like these jeans, we can give you a compressed representation of all of that data. And it's really useful for a bunch of other downstream teams to then incorporate into as features into their models, or as or in visualization, or in other sort of avenues where you need to work with other parts of the company, and you're trying to explain what kind of information we have and how well we understand them, and for driving trust with different partners. A second analogy I like to use, in addition to sort of like compression and a zip file, is coordinates on a map. And I guess Umap makes that a little bit more literally true, but in my experience, people are using embeddings as signals to downstream systems. But that analogy as coordinates on a map starts to break down, because each dimension is hard to interpret in isolation. But coordinates still naturally get you pretty quickly to like the ideas of clustering and structure. And because you're thinking of them as coordinates on a map, it also leads you to some like pretty quick, lead you away from some pretty quick gotchas. So for example, like using linear models like tends to like not work as well, because we can get into it, but like because you don't have this like linear structure. I guess it's sort of like a sort of recursive and arguing here, but it does, when you're thinking about coordinates, help lead you to thinking more about clustering. And then a third thing that I think about embeddings too, this is probably me going out a little bit more on the edge, is that they're a useful interface between teams within a company. And this is very, very particular to like my experience and the team that I led, which really felt by the end of it like feeling like embeddings as a service. And that's really useful because you are sort of compressing the data within your domain, within your product area, and then you're shipping it. So that way other people can implement and use those features without having to have a huge amount of specific context. And that's important because if you're, and this is now getting a long answer, so I'm going to let Leland talk just a second. I'm sorry, but it's useful because if you're an ML, your MO is to use as much data as possible, and that can be really tricky if it starts to reach across lots of different product lines, lots of different surface areas. It's a lot to keep track of, and embeddings can help break some of that up, and can help give autonomy to different teams, and can help simplify some of those dependencies. So anyway, so a little bit as a compression, a little bit as coordinates, a little bit as an interface.
Awesome. That's very, very, very interesting. And to extend the question for Leland now, I would like to know, how could you describe how an embedding relates to high dimensional data? And ultimately, what types of information or structure can be captured in an embedding? And is there any limit to it?
So I'm going to start that I guess I have a slightly more abstract take than Chris does. And for me, an embedding is really just any vector representation of data along with a notion of distance or dissimilarity that encodes or captures something of interest. And so that can include very high dimensional sparse data with Jacquard distance for like set comparison type things. I think Chris's point is well taken. That's still kind of hard to work with. So, compression is a useful thing. And so the key there is, do you want a compression that still preserves some notion of dissimilarity between the objects? So, for me, this is all very interesting because you're basically encoding the information you care about in this distance structure, which is really the topology of the data. And so that's where it gets interesting for me. What can you encode in that way? All manner of things, pretty much anything you want. If it's something you're interested in, you just need a way to inject that in. Now, to be honest, a lot of that is done these days with deep neural networks, which is not really my field, but you don't necessarily need that. A lot of things can just be encoded in terms of co-occurrence structure, or other simple methods will get you a long, long way. In terms of high dimensionality, if you want a simple distance measure, you want to use something like Euclidean distance or cosine distance or something you can easily encode. If the distance measure is simple, then you need a lot of dimensions to manage to represent your data in a way that encodes something interesting. And so that's the hard part. You can potentially have a lower dimensional data, but then you're going to need a much more complicated to describe distance measure between things. So there's sort of a trade-off there. And at the same time, just compressing everything down to very low dimensions, you need to sort of unravel a lot of the sort of topological structure involved. And there's always going to be trade-offs in that as well. So that's a thing that Umap tries to do is push things down to a very low dimensional space, trying to make the best trade-offs it can along the way.
Well, that's actually, I gotta thank you for that. I've never thought of it as a trade-off between number of dimensions, complexity of the metric. Like that's very, 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 very insightful. I want to move over because I also, now that we kind of laid the field of both a very practical way of thinking of embeddings and a very theoretical point of view, which I take joy in both personally. I would like to talk a little bit about, Chris, how do you go about leveraging embeddings like in your team, and what are your use cases in a more practical, real world-ish way?
Yeah, I mean, so I should say this is a team I used to lead, but it's probably not terribly important. But the way that this is consumed is essentially we build out like user and item embeddings, right? So what Stitchfix is essentially a personalization service for clothing. And what we try to do is try to figure out what your tastes are, and then try to send you clothes that you like. So not too dissimilar from Spotify, but for clothes, or Netflix, but for clothes. And what our embeddings are trying to do is trying to figure out what are your tastes and what kinds of items would you like, right? And so that's what those embeddings are trying to represent. Items that are similar in that embedding space will be co-liked, right? So that means that the same person, the same people are very likely to like both of them if they're close. And the same is true on the user embedding side. So if we have one item, then that item is probably co-liked by the same set of people. So and so that was the primary output of, and we called it latent style inside of our company. And that's the primary output of it. So we produce user embeddings and these item embeddings, and it would be consumed by a bunch of other downstream teams. So for example, a ranking team that tries to figure out like, great, like that just tells you whether these users and items are going to be liked. Will they actually buy it? Let's take into account price. Let's take into account fit. Let's try to take into account other sort of preferences and item attributes that we might not know about. Let's try to find a good stylist for you, right? So that's a totally different machine learning team within inside of Stitchfix, which would also consume those features. Let's try to find good email campaigns that you would like. Let's try to find good advertising that you might enjoy. Like let's try to customize a feed of content for you. Like it's just used, while it's collected in one place, the use cases are manifold and spread out a bunch of different places. So, and that's a really interesting and I think useful paradigm because, which kind of gets to like this pet theory and pet idea that I have, which is that embeddings are great for building autonomy, which I was kind of alluding to a little bit earlier. And maybe this only makes sense if you've been in a large organization, but if you're an engineer and your head's down and you're working on a project, it really sucks to get up, have to go ask for resources, or have to go ask for help, or have to go ask and get blocked because you aren't on a roadmap, or maybe you need like a tiny little bit of JavaScript code to be changed on a front end. And ideally, organizations are designed so that way you actually minimize the amount of like asking for permission and blocking that you get like this. And what I really enjoy in the world is when a good bit of technology manages to break down some of those barriers. And I think one of the things that you saw probably like 10 or 20 years ago was the rise of microservices. And what happened there was that these teams would spin up these APIs, these REST endpoints, or I guess more days like more GraphQL endpoints. But the point being that like they basically built a wall around their domain and say, this is the way you access our data. It's through this unified interface. You can't just reach deep into our databases and change things. And that gave them a great degree of autonomy to change everything within that set of walls. And I kind of wonder if embeddings aren't that for machine learning too, because they're providing the same sort of guarantees, right? They say, here's the compression of my data. Don't try to couple directly to the set of features. Don't try to like read, for example, a client's age. Here's an embedding that tells you everything I know about this person. So, and that allows all of these other ML teams to then use that data effectively and promote their part of the business without having to like have deep domain expertise on your part of the business where the data and the features are actually coming from. So I think there's something cool there. And I bet you there's something interesting intersection there with the rise of vector databases. Leland's working on Pine and Descent. Which I think is like a vector. Is that a vector search? Also, yeah. And so that's one of the ways that like we can serve embeddings faster. And I bet you that like there's something cool and rich at that intersection. If anyone's looking for a startup idea, that seems like there's something cool out there.
You imagine that we have a person that has a startup idea, like you mentioned, right? Like what advice would you give it to go from the Jupyter Notebook to productionalizing embeddings? What things to keep in mind? What is the three top advice? If there's any, it can be none, and just you can tell them to venture about it.
It's a lot. I think I don't know. Probably just remain skeptical is probably the biggest one, right? So I think it's maybe this is my coming as a scientist, but like there's a lot of weird things that show up with embeddings. Here, I'll tell a story that actually happened this week. So I had a colleague of mine show me a plot, I think of, I think it was like the norm of a set of vectors, and it was changing over time. And over the course of like a week, it like, I don't know, doubled. Don't know why. He looked at a bunch of different, or they looked at a bunch of different different categories within that vector space and try to figure out like, is it a specific area? Is it, what exactly attributed to this rise? And still hasn't found it. And so what I think is interesting is like, well, maybe this is actually maybe this is a good use case for Umap here, where we could actually try to switch from, well, we detected a problem. Now we need to like figure out and try to diagnose where the hell it's coming from. And I wonder, and I was suggesting to him like, hey, maybe this is actually a great place where like, if we can't actually identify a cluster by checking a bunch of categorical attributes that we know exist, like, well, like maybe it's one of the Umap clusters, like let's try to find it. And that's not crazy. And a lot of good stuff can come up from like looking at those diagrams, like looking at outliers, for example, is very, very useful, right? Like very frequently those outliers come from the model didn't train, or yeah, that like item got into our inventory, but we never showed it to anyone. And so it has this weird embedding, or that item has like something extremely wrong with it. And that's why it's out in la la land. And Umap can show you that. And I think it's, and I think it's a great way of like it's a great tool for the skeptic to use. So, but I don't know. Have you used it in that case, Leland, or is that, how do you use it?
So I and my colleagues tend to use it as a data triaging tool, much like that. I mean, for us, what Umap provides is a view on your data. It's not truth. There is no truth as soon as you represent your data in some way. You can take means and standard deviations of your data. That's a convenient compression because it turns it into a single number that you can use. Great. It's lying to you in some ways, as everyone knows, and so we just use Umap as another way to view the data and turn it into something that we can look at and sift through and not so much answer questions often as pose questions. How do you even know what questions you should be asking is often what we end up using it for. Let's just look at the data and see what's there and go, oh, well, I was not expecting that at all. Why is this here? Why is that there? What's this cluster all about? I need to understand that. So that's very much the sort of mentality we have with respect to it. And right now we're busy working on trying to get better at providing ways to understand what's going on in the UMAP plot. So maybe some sort of way to generate automated labeling over the top of your data. Like as in map style labels of, you know, countries and regions and whatnot. I want to be able to have like each cluster have some textual label that's referring back to the original feature space in some way. And as you zoom in, you know, you can get hierarchical levels of that labeling, or be able to have highlight a cluster and say, what makes this different? Why is this here? And I feel like those are the next steps, hopefully, in taking this sort of process. I think you were describing a very similar approach, you know, just look at it and start asking questions about it. So getting better at interrogating it is something that we're working on currently.
Because you mentioned hierarchy, and because this is also like a favorite topic of mine, you were mentioning earlier, talking about as embeddings as really defining a vector and a metric, and that's what defines an embedding, right? And which got me thinking, like, well, what are the different kinds of metrics we could use? And you saying hierarchy right now just once again triggered this thought that of this work now that's probably a few years old now of point array embeddings, and they have the really neat property. I guess this is also going back to old, at least for me, like old physics world, where as you go out in radius, you start to subtend like an exponentially increasing volume as compared to Euclidean space, which is, you know, growing cubically in 3D or quadratic, or, you know, to the fourth power in 40. But the neat thing about why you might want that is, and Leland, I'm sure probably already knows a lot of this, but like, is that it's really great for embedding hierarchies, because hierarchies, every time you go down one level, it grows exponentially as well, or, you know, if you're in a binary tree, it goes to 2 to the whatever. And I'm kind of wondering, is there a hybrid world out there, Leland, that we can have UMAP and have like, can we get like point array UMAP? Is that a thing?
Actually, yes.
Interesting.
We can embed via UMAP into theoretically somewhat arbitrary metric spaces. So in practice, the direct Poincare embedding is a little tricky. You need a coordinatization that works well with UMAP, and the Poincare disk is bounded in terms of coordinates, which is not so happy. But there are other convenient parameterizations of hyperbolic space you can use. I think there's some buried somewhere in the UMAP documentation. There's a demonstration where you can use a hyperbolic space embedding and then map that easily enough to the Poincare disk. But
wait, really? And it already exists?
Oh yeah, that exists. But you can also embed on other things like spheres and toruses and things like that. And I mean, at first that sounds like kind of a little bit arbitrary. Why would one care? But if your data is cyclic,
oh yeah, right.
Maybe you have some reason to want to map it into that.
Oh yeah, no, that would make a ton of sense if some of your like embeddings are, you know, day of year embeddings, for example, right? Or that would be fascinating, right? Like, which would presumably have to be. I mean, I guess it doesn't have to be, but it could be.
That is beyond interesting. I think one of the main takeaways of this talk is going to be use UMAP to pose the right questions. At least for me, I think even though I've used UMAP and I've come to ask myself questions, I think having it in the top of my mind, remind yourself this gives you the right question is going to be awesome.
Can I keep asking one more question?
Oh yeah, go ahead.
So what I really want out of embeddings that are hierarchical is, you know, to discover my hierarchy, and whenever we look at embeddings inside of Stitchfix, like at least on the item side, there's just a very clear hierarchy because our items are extremely hierarchical, right? Like we're pretty like strict down the middle. Like we've got men's clothes and women's clothes, and men's clothes break down into like tops and bottoms, and then bottoms break down into jeans and shorts. And what's cool is that like, oh great, like that hierarchy like maps to like individual clusters inside of UMAP. But you may not actually be able to see like the greater, like there, like for example, it's something as big as like all of bottoms or all of tops, like is probably going to be much harder to, is actually represented by like, I don't know, hundreds of small like UMAP clusters. So it gets a little bit harder to like actually discovered and like that kind of structure. I'm kind of hoping, like, I guess maybe the answer is go try it because it already exists. But like, I'm kind of wondering, is that something that a hierarchical embedding could help me discover and find?
Using hyperbolic space embedding?
Mm-hmm.
I don't know, actually. I'm off the top of my head, I couldn't tell you. I think that may be tricky. What you could do if you want to do something crazy along those sorts of lines is if you vary the number of neighbors that UMAP uses, it looks further and further out to try and establish what the sort of local structure looks like. So there's a big trade-off there, because it essentially smears out, flattens, averages everything within that sort of local structure range. So you can lose a lot of the fine-grained structure, but when it patches everything together, the more further out it looks, the more the patching together captures the sort of bigger picture global structure. So as you vary the number of neighbors, you're going to sort of probably move up through that tier of hierarchies. And if you want to play with that, there's an aligned UMAP module in UMAP, which lets you run multiple different UMAP embeddings, potentially of different data, but for now, let's just say over different parameters, varying in neighbors, and keep them aligned with each other. So what you could in principle do is run this aligned UMAP with a varying in neighbors, steadily increasing. And if you plot it out, a point then becomes like, if you imagine each 2D embedding sort of stacked on top of each other, a single data point then becomes like a trace or a curve upwards through that space. And ideally, you would literally see the hierarchy merging up towards a root in terms of clusters. So I do believe that might actually work. I've done that with the pen digits data set as a demonstration, and it does actually work. All the individual digits separate out and then slowly merge together into a common root. So presuming you have that very hierarchical structure, I think that might work quite well.
Interesting. Yeah, and I think that presumption is like very strong in our case. So I kind of hope it would work. How is that? So that sounds very different than like actually using point query embeddings or hyperbolic embeddings or whatever. How do you feel like is that intuitively different? Like it still feels like they sound technically very different, but I'm wondering, what was your intuition? And sorry, Kiko, I'm totally cutting.
It's okay. I can cut you in a bit, but so far, actually, my questions were in this line, so we're doing good.
But what do you like? But your hesitation was like, I don't know if that'll work if it's in hyperbolic embeddings. Is that a? Can you say a little bit more?
I guess I just don't. I'm not sure I see or can picture how that's going to come out in the representation you get, which is not to say that it won't, but it's not intrinsically obvious to me, which let's be fair, that doesn't I have not given this very much thought at all, but on an initial first pass, my thought was, I'm not sure I can see what would happen. I think you should definitely try it.
Great. Yeah, it's there. So now I feel like you should go try it. Yeah, those are the best possible answers. It's already there. You should go try it.
Awesome. I want to, because you mentioned a little bit about editing the number of neighbors, and I know, but I would like maybe Leland can talk a little bit more about it, about how you might have some certain hyperparameters that can move the attention from global topological structure to local, and that trade-off between the two. Would you develop a little bit more on that?
Yeah, so this is really the primary parameter to UMAP, is the n neighbors parameter. There are admittedly a lot of parameters in the Python implementation of UMAP. I just kept adding them because people asked for things, and it's like, well, I can do that. It's not so. but maybe it's a little overwhelming for new users. So mostly don't worry about all the other things until you have a really special use case, like you want to do a hyperbolic embedding, and then you'll care about some of those other parameters. But in neighbors is really the primary one you need to worry about. And it's really a matter of how far out in the space you're looking. So how to think about this. The data lives in some high dimensional vector space. And the thing to keep in mind is, hopefully, it actually intrinsically lives in a lower dimensional space. And what I mean by that is, if you looked at a local region of the data, it's not filling out all the possible directions in space all at once. If it is, then really there's not much you can do. Your data actually probably isn't very interesting because it's just a big ball. But almost always, it actually fills a smaller space at any local region. If you just look at a local region, it's a smaller space. Now, the catch with this mathematically is that you can look at a local region and it looks like a lower dimensional space, but then a different local region looks like a different lower dimensional space at an entirely different angle, if you like. And if you chose either one of those, the other one would look wrong. And this is why something like principal component analysis, which tries to project onto a lower dimensional space, doesn't necessarily capture these things. So what UMAP is looking to do is look at each local region and try and estimate what things look like. Try and look at the local structure there. And then it's going to glue all those different local patches together. And so, as I said, when you're looking at the local region, that's determined by n neighbors. That's how many neighbors of each point you're going to look out to define a local region of the space. And so if you choose a very small value, then you're focusing very much just on the very small scale local behavior around each point. And when you go and glue that together, there's not much overlapping between these different patches that you've created. And so it doesn't necessarily glue together in anywhere near as coherent a way to see the larger scale structure. On the other hand, if you choose a big n neighbors value, now all of a sudden you have lots of overlap between all your patches, and you're much more likely to glue them together efficiently into a way that's going to capture the big picture. The trade-off you're making with that is that, as I said, you're kind of averaging everything out within that local region. You're flattening it down so you can just look at it flat. And so any interesting structure on a scale within that neighborhood, you're going to lose. You're going to drop it because you're just flattening all that bit out. So there's kind of a trade-off as you go. If you want a larger, bigger picture structure, a larger n neighbors value is going to help. If you need the fine grained structure, a small n neighbors value is going to help. And unfortunately, you just can't have both at once. And so, this is when I said earlier, like, it's just a view of the data. It's like a lens. You're looking through a lens at your data, and it's going to distort stuff because that's what lenses do. The advantage is, if you choose the right lens, it shows you the things you care about and distorting away the things you don't. So you're just going to have to try and find the right lens through which to view your data, because no matter what you do, you're going to have some level of distortion.
So it's mostly like a confused. As you were talking, I think the analogy is pretty good. It's like, okay, you have your microscope, your lens, and you have your knob, which you tune to see what you want to see. Chris, I have because I've been wondering, you were mentioning also how you were actually asking Leland how they use Umap is for triage, and how do you do this in a real world setting, and how do you provide business value using Umap as if maybe in a bad way of saying a debugging tool or inspecting tool? That's a better way.
So so one of them, and I think Leland had the term triaging, which I think is fantastic. I really like that. So one of them is that. So it's like engineer, scientist in a notebook, working like in by themselves or with some close colleagues, trying to figure out like what's up with these embeddings and being skeptical about them, looking at the outliers, trying to like, do these clusters make sense? Do they not make sense? Is this the structure I expect to come out of this? And then being very critical about it. I think that's, just being a good scientist and having a good instrument with which to go do science. Aside from that use case, there is, I think, trust building is very, very, very important, and in particular with non-technical partners. It's one thing to say, hey, we took this transformer model and we built some embeddings and it's got this amazing scores, AUCs, and the partners have no idea what you're talking about, right? Like, they're experts in merchandise. They spent their entire life building relationships, or their career building relationships and building, I don't know, supply chains to try to get that out here, and they're not going to understand any of the words that I just said. But so it's like, great, well, how do you still build trust? Right? You're both experts, you're just in wildly different domains. And I think that's what Umap is very amazingly useful at doing. It builds a map, right? It builds and maps are some of the most visually stimulating things that you can possibly produce, right? It's so much more engaging than a bar chart or a scatter plot or saying that your AUCs are amazing. It really helps someone delve in and says oh yeah, I get it. Right? No one's ever said after I brag about our bajillion parameter model, how amazing it is that they get it, until they see a UMAP and they're like, oh, right, these things are close together. Yeah, that makes sense. A person that likes this would also not like this. And that's really special, right? Because it takes a lot of effort to connect two very deep domains that are otherwise very disparate. And so there's a lot that goes into building trust and into building really effective visual communication tools, which I think is, UMAP is premier among them. So one of them is sort of the engineering challenge of fixing stuff in your data and your noise, which is, obviously a huge part of being a scientist and being an engineer. The other one is more about working with folks and being effective within a greater group than just yourself. And it's really cool to find a tool that does both of those things.
Very, very uncommon also, right? I want to almost pose the same question to Lina, because I'm assuming that your problems are slightly different, and this is me guessing, so that's why I'm asking a question. When you use
Leland, you don't sell clothes?
Oh, now I got it. Yeah, so I was thinking, do you use UMAP to improve UMAP? Are you working on another tool and UMAP is still useful? How do you go about it? How do you use it in case that we have more research oriented people in the audience?
Yeah, so I'm coming from a research-oriented perspective, and you always need real-world problems to motivate your research, right? You can't just work in isolation. So, we reach out to people around us who have interesting problems, and they pose their problems to us. And the reality is that comes with data, because you need some data to work with. And one of the first things you realize when you reach out to lots of different people for data is that everyone's data is different, and that I don't understand any of it. And so, so my colleague John Healy has a mantra: look at your data, because we'll get some data from people, and we'll ask them a bit about it. What can they explain about the data? And there's normally a bunch of assumptions that they inform us that are definitely true. And so the first thing John will do is demonstrate to them that, in fact, all of those assumptions are false. It's almost always the case that when when you're a domain expert and you've been looking at data, ultimately it's kind of like looking at it through a straw, right? You're looking at tables, you're looking at the bits of the data that you can work with, and you mostly know how all the data is, but there's all the weird bits and pieces, and they always violate all your assumptions. And so the only way you can get anywhere is to try and look at your data and ideally look at it in the whole. And that's where UMAP is useful, because rather than like sifting through a little bit, you can look at the big picture and start asking interesting questions and start trying to understand your data. So for us, UMAP's a tool for people who don't have any understanding of the data set to at least get some leverage into what sort of questions should we be asking about the data? How can we start understanding the data better? Because really, understanding the data is the first step for anything else we want to do downstream. Do we want to do some fancy machine learning task on the data? Well, we better understand a little more about what the data looks like before we just shove it in a model, because otherwise bad things are going to happen, or we're just not going to know that bad things are happening and they're going to quietly happen. So really, it's a data understanding technique for us. And I mean, it's one of many tools you want to use. It's not the be all and end all. As I said, it's going to lie to you about your data in various ways, but it's also going to highlight things about your data that you're not going to find otherwise. So it's an excellent way to just get started understanding your data. So that's it for us. It's data triage and understanding.
Awesome. Last question about the whole inspection. We've been talking about data sets and using UMAP for data sets. I want to go back to the embeddings discussion we were having just a few minutes ago. How would you tell somebody, okay, I have different versions of my embedding. What does that version of the embedding actually depends on? It does depend on the model. Of course, it's gonna, different vectors gonna come from different data. But besides that, I'm assuming that the model version changes. Whether you change the model, the embedding vector is gonna be, the compression tool is gonna be different. And how would you go about comparing two different embedding representations of potentially the same data set? Which one is better? How would you go about it? Maybe Chris can start with this one.
Yeah, sure. I don't actually know if I have a lot of good answers, except that it's a problem that is severe and happens very frequently, and has even more flavors than the ones you pointed out. So I think versioning embeddings is tricky, and it's the thing you have to deal with if, for example, you are trying to build embeddings as a service, right? Which is the role that we played. Versioning is tricky, right? Like not only that, but we're trying to embed a matrix factorization type problem. So you have to embed both the users and the items, which means that like if one of those things gets updated and the other one doesn't, you got problems, because what matters is the dot product between those two things. So that's a place where things can get out of alignment, both because you have, in this case, two different spaces, which both live in a greater embedding space, but it's still very easy for those two things to fall out of alignment in production. Another one is, and sort of similar, is like a training serving skew. Like you have one set of those embeddings after your model is trained, and then once your model is deployed as a runtime service and spitting out embeddings continuously, it may not line up with the embeddings that are in the trained model, because maybe in the meantime, your trained model has run again and it has now slightly incremented its version. Or maybe you actually pushed out a new change to the model. It didn't just encounter new data, but like maybe you actually have like a major version to the model. And so keeping all those things like in line is a big deal. And having to, right, because they're all sort of like, it's the Cartesian outer product of all those things, right? So it's like training serving skew, like users and items and version changes with new data. And then you have version changes with like the actual code changes. So all of those things are really tricky to line up. And UMAP is one of the tools that like you can use to like try to at least tell that things have changed. But we'll also use whatever other tools we can, like easy other like metrics. Like we will just measure the means of vectors. We will measure like the norms of things, just because they're simple. And when things deviate, well, you better at least you have some sort of detection. What's terrible is when you don't have a detection. That leads to lots of problems, which obviously Arize helps us do quite a bit.
Awesome, thank you for that. So, we thank you for being generous with your time. So I want to have maybe a couple questions. I have one for each about future. Like how do you see this path going? Leland, I am curious about what do you think the future steps for lower dimensional topographical analysis of our data sets is, or if you can develop on out on that line, it's kind of an open question, or if you want to see maybe how could you, because it could be any tool that you're aware of, but if we want to down it to specifically to UMAP, what areas of UMAP should we encourage maybe potential grad student or potential researcher or somebody with a lot of curiosity that they can actually try to improve? Where do you think the future going?
Okay, well, I'll try and tackle a little bit of both. So I think there's actually a lot of really interesting work going on in topological data analysis right now, but a lot of it is actually still in the very abstract stage. So I can't really see it showing up on the production pipeline anytime soon, but the ideas are very, very powerful. And so I think there's a lot of work on hypergraphs and simplicial complexes going on in the theoretical community right now that's really interesting. And then there's a lot of work on sheaves and cellular sheaves, which is a very abstruse mathematical thing, but turns out to be surprisingly useful. And they have a lot of relations to graph neural networks, it turns out. And so you can see some of these ideas actually show up in the graph neural network literature. And I guess that's some of the ways in which some of this topological analysis is going to slowly flow in. There's a lot of interesting work there. So I'd look out for those terms sort of slowly leaking their way into the sort of more mainstream machine learning community. In terms of where UMAP is going or could go, so I want to give a shout out to the parametric UMAP, which Tim Sainberg worked on and contributed to UMAP. It provides neural network trained to learn a UMAP embedding directly from original source data. And to be honest, I think it's vastly underused. I think what Tim did is amazing, and I haven't seen it used anywhere near as much as it should be. Because one, it supports incredibly fast inference, but he did some work on semi-supervised learning, which was providing very impressive results, and autoencoders using UMAP as a loss within the autoencoder itself. I think there's a lot of interesting work in there that could be extended a lot further by playing around more with the capabilities of that sort of approach. And then lastly, I'm very interested in how to align different UMAP models. So there is an aligned UMAP, which can align data that you can explicitly define a relationship from one data set to another. But what if I just start with two arbitrary data sets, say word vectors from French and word vectors from English, and no dictionary? How do you produce a UMAP embedding that aligns those so that I can embed both? And there are ways to do that. Gromov-Wasserstein distance is the magical search term for that. And I think that's a coming thing that's going to crop up soon, is people are going to align all these different multimodal data sets via these sorts of techniques. Now, right now, I know there's been some impressive work with neural networks, like Clip from OpenAI, for providing this sort of multimodal embedding. But I think there's going to be a lot more of that, and I think it's going to be able to be done with less giant neural network training resources than OpenAI has at their disposal via some of these other sorts of techniques. So I think there's a lot of interesting directions that could go, and I think UMAP can play a role in that if somebody's interested in looking into that further.
Wow, both of those are really fascinating. I mean, I remember the old WordDevEc paper had like a learning from English to Spanish or English to French, and they learned like a rotation matrix, which took the one to the other. But what you're suggesting sounds like you could actually do that in almost unsupervised or presumably unsupervised context, which sounds unbelievably powerful. Like that would be great. Like, because from the industry standpoint, like that could mean that like, I'm in the recommender world, like you could build a recommendation engine with almost no data or with literally zero data, right? And so like that could be incredibly powerful and like really could remove like one of the largest problems that all recommender systems start out with, which sounds really fascinating. And I wanted to also comment on one other thing too that you said, which is that like the parametric UMAP is, and the fact that like that UMAP actually has a learned function built into it is one of its superpowers too. And it didn't go lost on us. Like it is unbelievably useful to train UMAP and then be able to use that to reproject new data points onto the UMAP. That is very, very valuable in exactly the kinds of debugging and triaging situations that we find ourselves in, when things change in time. So I also wanted to +1 your comment, Leland, that like it is not lost. it is in fact quite useful, and I would say that I have used that a lot. That specific feature makes it, for example, very, very friendly towards engineering use cases. And when I think of like UMAP and you and your colleagues' work as being extremely practical and utilitarian, like I think of very specifically that particular feature.
Well, then I want to ask you the same question, Chris. Like, where do you see, well, for you, it was like embeddings as a future, not only where do you see it going, or maybe where you would like it to go?
Yeah, super cool. All right, so I definitely got my pet theory that embeddings are a great way to interface different teams. There's no real tooling around that. All right, like if we use a microservices analogy, like there was a lot of tooling to go build a Rust API and then help build SLAs around that, right? To help like people keep their contracts, to help build autonomy. And so I think there's something there. But one thing that's obvious is that there's a big rise of vector databases, which are essentially building indexes on these embeddings and make them easily retrievable, fast searchable. And that's at the core of many search and recommender systems. And I believe search and recommender systems to be like one of the foremost like machine learning use cases. So still feels very early days and very immature still. So I think there's a lot to be done there. That gets me really excited. There's this other idea that Eric Bernardson on Twitter like was throwing around, which I'm also particularly fond of, but I can't claim that I came up with it myself. Is a database which kind of like vector databases has embeddings as a natural concept, but really like as you insert data is computing the embeddings on the fly and using them everywhere, right? So if you've got a text field, well, here's the embedding for it. If you've got images, here's the embedding for it. And that really helps you immediately turn a database into, for me, like a recommender system. And I think there's a lot there that could be really cool, and that would, I think, help simplify the unbelievable amount of problems and challenges that you run into when you're trying to train and deploy your own recommender system in the real world. So I think there's a lot there.
Awesome. Well, thank you so much. I think we're gonna have to conclude with this panel. Both the audience and I appreciate you being here. As I said, we're over time, so you're being so generous with your time. We appreciate it. Personally, it has been my privilege to have you here and ask you questions. I hope to be talking to you soon. Well, thank you so much, and bye, everyone.
Bye-bye. Take care.